Hello and welcome to this webinar from Lightnovo. A couple of housekeeping notes before we start. Please keep your microphones muted and the cameras off. So let me share my slides. So this webinar is entitled Handheld miniRaman Spectrometer. A couple of words about our company Lightnovo EPS. Lightnovo was founded in 2019 by our CEO, Alexey Ilchenko. And our mission is to democratize the power of high-end Raman spectroscopy for the benefits of mankind. And by this, we mean that we make Raman spectrometers more compact, more affordable, without the compromise in quality. And as well, we broaden the range of applications. Our headquarters are located in Birkerød, Denmark, in the suburbs of Copenhagen. We as well have a branch in the UK, Lightnovo UK Limited, as well as multiple remote employees working remotely from Ukraine. So let me go through the basics of Raman technology. In Raman spectroscopy, the sample is irradiated with a laser. You can probe various different types of samples, solid state, powders, liquids. You can probe through the container like a plastic bag or a bottle. You can basically measure everything except of metals. As you know, during light scattering on the sample, there are multiple components. First, there is relay scattering without the change of laser wavelengths. And then there is Raman scattering with the change of wavelengths. There is a red-shifted Stokes component and a blue-shifted anti-Stokes component. In our technology, we focus mostly on the Stokes component. Each compound has a unique vibrational fingerprint. And with this fingerprint, the compound can be uniquely identified. So the Raman signal is collected by the spectrometer and then is analyzed by artificial intelligence, which performs the search in the library of compounds, and so the substance can be identified. Here's an overview of our product. Our core product is miniRaman. miniRaman spectrometer is a compact handheld spectrometer suitable for field operations. Then there is a miniRaman microscope. miniRaman microscope is a compact portable microscope, which, for example, can easily fit into your backpack. One of the potential applications is the use in mobile forensic laboratories. I'll perform live demonstrations of miniRaman spectrometer after I show all these slides. So another line of products is RG Raman spectrometers and microscope. RG stands for research grade. And here you can have wider choice of wavelengths than in miniRaman spectrometer, because you can use different other lasers which are less compact. So we as well have TOR. TOR is a Raman microscope with polarization capabilities suitable for advanced researchers. With TOR, you can look at the polarization dependence of Raman scattering, and it finds its applications in the field of crystallography. So what we want to do in Raman spectroscopy is we would like to perform a revolution similar to what was done by the smartphones in the field of photography. Sorry, I see that someone is not muted. Could you please mute? So basically, we want to perform a revolution in Raman spectroscopy similar to what was done by smartphones in the field of photography. Basically, nowadays, most of the users use smartphone cameras for photography in everyday life and rarely use DSLR cameras. So the advantages of miniRaman: it's a quick start, operation readiness 5 seconds, small size, can be carried on a belt, for example, by a police or customs officer, and low price starting from 10,000 euros. It is as well highly reliable and there is no need for recalibration. miniRaman is protected by various international patents. Uh, as well, we have recently published a paper in Nature Communications where we describe the core principles of miniRaman technology. The key feature here is the presence of inbuilt reference channel with a polystyrene sample. This allows us to use smaller, less expensive lasers without thermoelectric cooling. Uh, the spectrometer can be with one laser or with two lasers. The main 785 laser gives the spectral range from 400 to 2700 wave numbers, while an optional 660 nanometer laser gives the spectral range from 2700 to 4500 wave numbers. The X and Y calibration is performed in real time. And as you can see, this allows to get us very stable Raman spectra, even for very unstable lasers. So here we see an overview of mini-Raman models. There is mini-Raman standard with one laser, 785 nanometers, with power 5 to 50 milliwatts. mini-Raman power, also 785 nanometers, but with increased power specifications up to 90 milliwatts. mini-Raman SERS, it's again 785 laser, but with power well tunable in low power range, suitable for surface enhanced Raman. mini-Raman standard dual with additional 660 or 675 nanometer shadow, and mini-Raman power dual with increased power in the second channel, 660 or 675 nanometers. So basically, we have developed various accessories for mini-Raman, probes with different working distances, ranging from the touch probe to the probes with middle working distance, 10 millimeters, and long working distance, 25 millimeters, as well as accessories for measuring in liquids and in powders. We also have a precise focusing stage for precise focusing on a sample. You can check our YouTube videos on these different accessories. After the webinar, we'll send you the link with basically the PowerPoint presentation where you can follow the links and watch the corresponding videos. Additionally, we have recently developed a standoff accessory for mini-Raman for the sensing of hazardous substances. Basically, it might find application in this field. It has a working distance of 1 meter. So it's also possible to integrate because of the lightweight. It's 250 milligrams when performed in the frame of aluminum. It's possible to integrate mini-Raman on a drone, for example, and this could be useful for CBRN applications. So mini-Raman microscope. I have already mentioned that, but as you can see from this slide, the mini-Raman microscope, it's a modular system where mini-Raman spectrometer goes inside of mini-Raman microscope. It's also protected by international patents, and has all the advantages of miniRaman spectrometer, like built-in self-calibration and ease of use. We have a whole ecosystem of software, MiraSpec software. It's the software on the device, so firmware and embedded Linux software. We have the applications for the mobile phone and tablet, as well as desktop applications. And it's the same software system which controls all of our products. So the use cases for miniRaman spectrometer are identification of toxic gases, chemical weapons, explosives, illegal drugs, hazardous liquids, as well as bacteria identification, microplastics, polymers, art objects, study of minerals, skin analysis, analysis of plants, food analysis. So here's an example of bacteria identification with miniRaman spectrometer equipped with a microscope objective. Here we were able to identify different types of bacteria. You can check an application note on our website as well as a video on YouTube if you are interested in this specific application. Then with miniRaman, it's possible to study skin and to perform diagnostics for skin cancer, for example, or atopic dermatitis. We have as well, we have a video on YouTube and application note on the website. With miniRaman spectrometer, we also performed some studies of cannabis plants. Here, 8-30, we figured out that 8-30 nanometer miniRaman modification became more useful because when we measured with 785, we got quite some fluorescence, which is basically hiding the Raman signal beneath it. And when, as you know, when you go more to the infrared with excitation, you minimize the fluorescence and improve basically signal to noise ratio in Raman. So we were able to study the concentrations of THC and CBD. And as you know, THC is an illegal compound and CBD is a legal compound. So we also studied freshness of meat and fish with miniRaman spectrometer, and you're welcome to check our YouTube video on that. Another application is quantification of nutrients and metabolites during fermentation by miniRaman. And again, we have an application note on that on our website, lightnovo.com. As well, we are able to quantify the concentration of toxic methanol in alcoholic beverages, such as vodka and whiskey, using miniRaman. So here are the list of some of our end users and application cases. I cannot name the companies and organizations because of the NDAs with them, but basically in Sweden, they are measuring toxic gases. In the Netherlands, they're doing some bacteria identification. There are multiple users in Denmark, study of gases, offshore research, skin analysis, biomaterials, cannabis. In the UK and Ireland, they use miniRaman at the universities for teaching and R&D. In Canada, for example, miniRaman is used for some space applications. In the US, miniRaman is used for SARS and toxins identification. And in Australia, miniRaman is used for the inspection of concrete. So with this, I conclude with my slides, and I would like to say that we are open to collaboration. And now I will perform the demonstration of miniRaman spectrometer. If you check my video on the camera, I have a miniRaman spectrometer in my hands. Let me share the screen with miraSpec software. So here's miraSpec software. The spectrometer is connected. Now I will start the laser. So the 780, we can adjust the exposure. Let's put it to, I don't know, 1 second to make it optimal for different samples. And as you can see, we maybe, sorry, it was 100, 1000 milliseconds. Here it's 1 second, and we have two different traces in the graph. So the red is the background signal. It's actually because there is some sunlight in the room, and it's from the sunlight, which is the background in Raman. And the blue trace is the signal from the inbuilt polystyrene sample. The spectral range is from 400 to 2500 wave numbers. Then I can switch to the 660 nanometer laser. And again, here we see the signal from inbuilt reference sample. And basically what the device is doing, because the lasers, the small lasers which we use, they are not semi-electrically cooled, because you cannot put cooling like that in a small package like this. And then there is also, because this supposed to be battery powered, then the lasers are drifting around and mode hopping, but everything is compensated when we look at the reference channel. So basically everything is stabilized, because we know that in the reference channel we have polystyrene sample, and then embedded software is performing all these corrections and calibrations in real time. So let's measure some samples. What I have here, I have acetic acid in a vial, and let's measure the sample. And actually currently I'm using the probe with the working distance 1.5 centimeters. I switch back to the 785 nanometer channel, and as you can see, we have a signal. Let me hide the reference spectrum. So now we have the signal from acetic acid in the range of in the fingerprint range. We can now switch to the 660 laser, and we get a signal in the range from 2600 to 4000 wave numbers. So this was a demonstration with the liquid. Then what I also have, I have some white substance in the back, and let's try to identify what substance it is. And for this, I'll use a contact probe. So now I'm changing the probe. I attach the contact probe. I start the 785 laser. And what is actually useful for substance and identification, for more precise identification, it's useful to record the background. So I'll perform the recording of the background. I'll cover the sample, the spectrometer with the black tissue to protect from the sunlight and have pure background from the probe. We go to the background correction tab and I click, maybe let's put it to 2000, the exposure time 2000. Now I click capture. So the background is captured for 785 nanometer channel, and we'll perform the same. Well, it's not necessary for identification. For identification, we only have the fingerprint region. So, but I can just show to you that we can perform background correction for the other channel as well. Oh, sorry, I clicked reset. Now we have to capture again. Capture for 660 channel. And back to 785, we capture and we click enable. And as you can see, the signal is at the 0 level now. So then I take this plastic bag with white substance. I push it against the probe, and we already see some spectrum with lots of peaks. We can actually automatically fit the window, so it's easier. Then we capture the spectrum with adding to data analyzer. Capture the spectrum. Spectrum is captured, and let's call it O1. And let's try to identify. We go to identification, identify. And it says so basically the artificial intelligence built in our software is performing the session library. And it says that it's acetaminophen with the probability of 95.8% or paracetamol with probability 93.9%. And actually acetaminophen is just a different name for paracetamol. And somehow in our library, we got measurements of these two compounds from different brand names of the same chemical substance. And on the back, it's actually written paracetamol. Let's try to identify another compound. So I have another plastic bag with the white substance, and so I push it against the probe. Here's the spectrum, as you can see. Sorry, there is some problem with my computer because I cannot click on anything. It's probably because I'm sharing the screen or something. Basically, as you can see, with another compound has a completely different spectrum, and then we can also identify that. So basically, that's what I wanted to show. And if you have any questions, you can type them in the chat, for example, now, or you can just ask them, but not all at once. Any questions?
Hi, Olin. This is spoken from India. Uh,
Okay,
yeah, hi.
hi.
Yeah, this was a nice presentations, and I'm really happy to see such a small mini Raman spectrometer. And I have a few questions like, what is the resolutions of the uh, you know the spectrometer? Like,
The resolution of miniRaman, it could be down to 6 wave numbers.
six number. Okay,
So in
that's
the
nice. Right.
specifications is 6 to 15 wave numbers, and then it's actually sometimes a trade-off between the throughput and the resolution. So for some
Right.
applications, you need more throughput, then the resolution would be worse. So we can tune
Right.
that.
Okay. And you said the spectrometer has a library also for chemicals. Like, does it covers like what is the range? Like, does it covers like the explosive and like all kind of chemicals? How big is the library?
So we have at the moment we have quite uh, simple library with hundreds of compounds we had access to, and then we collected ourselves. But we're also integrating third-party library with up to 15,000 compounds, and uh, basically it has sub-libraries with different types of classes of compounds. For
Right,
example, toxic chemicals, explosives, narcotics, um, as well as polymers, and so on.
right.
And then the end user can choose which type of
Oh,
library to
based on their
purchase. Yes,
based on their applications.
their
Right, right,
application.
right. Okay, thank you for
You're welcome.
clarifying the queries. Thank you.
Any other questions?
We have questions in chat. Please check.
Yes. Ah, there are questions in chat. Okay, there are 4 questions. Is it possible to do only single point measurement? You don't have any equipment for raster scans. So basically, well, with as what I understood, with miniRaman, we do single point measurement on a single spot, but we have equipment for scanning. It's our microscopes with automatic XYZ stages. Next question: how do you recommend to adjust the power of the laser? So basically, it depends on your application, and then our miniRaman and other spectrometers, the power is adjustable, and it's basically you would like to have the power as high as possible to get better signal to noise ratio, but not too high, so that you won't damage or modify a sample. So you need to study what's the damage threshold of the sample. It's basically probably measuring at low power, then going to high power, comparing the spectra, and so on. So it requires some research. Uh, it is possible to the next question. It is possible to quantify the amount of a certain compound, as you mentioned in one of the published results. Can you provide an example with the software? It is possible to perform well, demand, is it possible to perform continuous measurement of a material, for example, during its elaboration? So basically, yes, we have a tool to do time scans. So basically, you just monitor the Raman spectrum over time. And then the question before that was about quantification. Yes, it's possible to quantify the ratio of different compounds in the sample. but then in reality, you would need to know what type of compounds you have, and then to do some analysis with also chosen algorithms that work for your application. It could be like principal component analysis, could be something else. Next question. Thank you for your presentation. I'm just wondering if you talk about mapping capabilities and the spatial resolution for the miniRaman microscope's precise NRG products. Thank you. So basically the spatial resolution is diffraction limited. So for example, for 785 nanometers, then you have lambda over 2, so like 400 nanometer spatial resolution. Do you have any experience with the analysis of liquid food samples? In principle, I would say probably yes, but you can just follow up by email and we can discuss it. We can either reply by email or arrange a separate meeting if you are interested in this specific application. Then next question, a spectral range from 2500 to 4500 wave numbers. What purpose for this? Is this misunderstood your slide? So basically from 2500 to 4000 wave numbers, for example, you have CH stretch region, you have water peaks there. So it's not for substance identification in most cases, but then you can do some research in that region. Next question, is it possible to use data with Python? Yes, and actually me personally, I'm always analyzing my data with Python, and the software it allows to export to TSV format, which is tab separated values, and then you can load it in Python and you can analyze your data there. The same goes for microscopy data and so on. How accurate could be AI estimation for complex biological samples like skin cancer, health skin? So basically, again, it very much depends on the specific application. And for AI, it's how well you choose the model and how much data you collect, how you train it. And at Lightnovo, we have real AI and machine learning experts. And if you send us an email, we can discuss your application and ways to analyze data. Next question. Thanks for the excellent presentation. Two questions. Have you considered integrating the Tic-Tac spectral library, a library of NPS? When would you have the functionality of quantitative solving mixed samples? Okay, we are now integrating. I've never heard, me personally, I've never heard of Tic-Tac spectral library. Maybe I should actually write it down and check what it is. Tic-Tac. But we're integrating the ST Japan spectral library at the moment. Then regarding the mixture analysis, we already have this functionality. We're constantly improving it, but we do have that. Can we run a sample at low frequency, like a 5 wave numbers to 150 wave numbers? Also, can we attach on-dex low frequency probe? Thanks, Hiroshi. So basically, we don't have such an opportunity, unfortunately, with miniRaman to go to small Raman shifts because the laser is unstable, so it's moving in that spectral range and then it's cut off by the filter. That's why we start at 400 wave numbers actually. We can maybe improve the devices in next iterations, and then we can shift maybe to 200 wave numbers, but not to low Raman shift range. For that, I recommend our RG systems, where you can look into that. But Ondex low frequency probe, I've never heard of it. Maybe if you send me an email, then I can check it, and we can discuss. What is the maximal distance for the measurement? So basically, with the standoff probe, we were able to measure from the distance of 1 meter, but the signal, it also scales, it also goes down when you increase the distance. So for some specific applications, you can measure at long distance, but you lose in sensitivity. What is the, no, it was, can you tell me what is the trade-off when you're using standoff probe? How do you focus at a distance? So basically, I already answered this question. And about focusing at a distance, just adjusting the distance between, and then our standoff probe, it has basically variable focal distance, and this way you adjust the distance. So no more questions. Then I would like to thank you for your attention, and then we'll follow up with the slides. So we'll send you the slides, and we hope that the recording that everything was recorded well, and we'll upload this webinar on YouTube, and we'll send you the link to this as well. Thank you.